Hello and welcome to Chemistry with Dr. Clark. This video we're going to talk about using Hess's law to calculate the heat associated with a chemical reaction. Okay, so I have a few examples here, but there are a few background rules that I think that we should probably cover first. So let's say that we steal this first given reaction. Okay, so if I rewrite the first given, that's an H2 gas plus a half of an O2 gas, turning into an H2O gas, and the delta H is a minus 285.8 kilojoules per mole. Okay, so if we are going to do some Hess's law, basically it's kind of like solving systems of equations. So in math class, if you've got a couple of equations and you want to put them together, you can use like substitution or elimination to put them together. And in order to do that, you often have to make changes to the equations. So Hess's law is kind of the same, right? In Hess's law, I'm going to give you a bunch of equations. I'm going to ask you to make whatever changes to them are required, so that way when you add them all up, you get this equation. Okay, so I want to add these three equations to give me this one. And in order for them to add to give me this equation, I may need to make some changes. Like for example, you can see that there's hydrogen gas here as a product, but I have hydrogen gas here as a reactant. It's on the wrong side of the equation. So often I will have to take my equations and flip them. Sometimes the numbers are not right. See, I have CH4 here and I have two of them. But in my equation, I've only got one, right? So I need two. So if I'm going to be doing some Hess's law, I'm going to have to take the equations that I'm given and perhaps do some modification. So the first modification that you often have to do is take the whole thing and flip it. So your products become reactants, your reactants become products. So let's do that. If I put my water over here as a reactant, I put my H2 gas and my 1/2 O2 gas as products, then I have just flipped the entire equation. Now, if you flip an equation, you are now running the whole thing backwards. Okay, so let's say we talk about ice for a minute. If you have a cube of ice and you are going to put heat into that ice cube to turn it into water. So let's say that you had to add 100 joules of heat to turn the ice cube into water. Well, if you want to reverse the process, turn that water back into ice, it kind of makes sense that you'd have to remove the exact same amount of heat. If it took 100 joules to melt it, then you should have to suck out 100 joules in order to freeze it, right? They should be opposites. And in the world of chemistry, if you put heat into the ice cube to melt it, that's a positive. But if you suck heat out of water to freeze it, that's a negative, right? Heat in, endothermic, is positive. Heat out, exothermic, it's negative. So if you're doing the exact opposite process, you should get the exact same number, but you should get the opposite sign. So when I take this equation up here and I flip it around, then my delta H should change sign. So instead of a negative 285, it should be a positive 285.8 kilojoules per mole. Okay, so flipping equations, perfectly acceptable. You just can't forget that you're going to be changing the sign. Now, the other issue that shows up sometimes is, let's say I don't want one water. Let's say I want 3 waters, right? So I would like this equation to involve 3 waters. Well, if you think of this like a math equation, you're allowed to do anything you want to both sides of the equation as long as you do the same thing to both sides. So if I've multiplied the reactant by 3, that means I also have to multiply the products by 3. So I'll get 3 H2s. I'll get 3 times a half of an O2 gas. And if you're doing this reaction 3 times as much, you should get 3 times as much entropy, 3 times as much heat. Right? Think of it like a campfire. If you burn 3 times as much wood, you should get 3 times as much heat from it. So this delta H should be 3 times 285.8 kilojoules per mole. Now, for this reaction here, the per moles is a bit of a fluid thing, right? For this reaction here, this is a formation reaction. You are forming water, and you are only forming one of them. That's why this is a kilojoules per mole. It's kind of like a formation. This is almost a delta H of formation. Okay, that's why it's a per mole. If you are looking into heats of formation and the reactions that go with heats of formation, there is another video that talks about calculations involving heats of formation. But the reason why I mention that is because here you are forming one water. The water is the most important thing, hence the kilojoules per mole. This reaction, when you flip it around, is more of a decomposition. You're taking the water apart, but still the water is the most important thing, right? So there's still one of them. That's why it's still per mole. But the minute I multiplied it by 3, there's not one of anything here, right? There's not one water, there's not one hydrogen, and there's not one oxygen. So really, this is no longer kilojoules per mole. It's just kilojoules. So when you find these problems, you'll often see that some of them start out as kilojoules per mole, but the per mole often gets dropped pretty quickly, especially the minute you start multiplying things out. Okay, so the per mole part is fluid. It's there and then it disappears. Okay, so those really are the 2 things you're allowed to do. You're allowed to flip the equation and change the sign, or you're allowed to multiply everything by a number. Okay, that's the 2 rules. All right, so let's say we come back to our problem. Now, if I'm going to do this, I like to do it systematically, right? I like to approach the problems the exact same way every single time, because once you get into a pattern, you have less chance of getting lost or making mistakes. Now, that's not to say that your Hess problems are not going to be tricky. Okay, Hess problems are like little puzzles. Even though you know the rules, you're allowed to flip equations, you're allowed to multiply it by a number, each problem is going to be unique. And what I find with Hess, the more Hess calculations you practice, the better you get, because you start to see patterns. Okay? But if we work our way through this, I'm going to look at each chemical in my target equation. I'm going to call this my target equation, because this is what I'm aiming for. When I add all of these equations up, this is what I want it to look like. So in my target equation, the first chemical is CH4. There's 2 of them, and it is a reactant. So what I need to do now is look through all of my given equations and attempt to find CH4. So if I look through all of my equations, I can see that the CH4 is here. Okay, now that's great. The 2 things that I need it to be is in the right location, reactant versus product, and I also need it to be the right number. Now, one of those 2 is good. I need it to be a reactant, and it is a reactant. That's excellent. The problem is I need 2 of them, but I've only got 1 of them. But like I said a minute ago, that's not really a problem, because I can just multiply this by 2. Now I have 2 of them. I needed 2, and I have 2. But if you're going to change one piece of this equation, you are going to have to change it all. So you're going to multiply everything by 2. So you had 1 and now it's 2. 2 times 2 is 4. 2 of those. 2 times 2 is 4. And you're going to multiply this by 2. Now, I have a suggestion. Like, multiplying this by 2 doesn't really make the givens that messy. But if I start flipping things, it's going to be really hard for you to keep track of the changes that you've made. So my suggestion is, once you've decided how you're going to change the equation, rewrite it. So I've decided I'm multiplying the whole thing by 2, so I'm going to rewrite it. 2 CH4 gases plus 4 O2 gases turn into 2 CO2 gases, 4 H2O gases. Now, it is important to write solid, liquid, or gas, because for some of these, you will get the same chemical, but in some places it's a liquid, some places it's a gas, and those are not the same, right? They're going to be different. And I'm going to take my delta H, and I am going to multiply by the 2. So if I pull out my calculator, that's an 890.4 negative times by 2. That gives me a negative 1,780.8. Now, it did start off as kilojoules per mole, okay? It is a combustion reaction, right? This was methane being burnt. And because the methane was the most important thing, as long as it had a 1 in front of it, it was per mole. But the minute I changed it to a 2, I'm just going to drop the per mole part. Now, see how I put a nice little blue box around it here in my target equation? Let's put a little blue box around it here. Because it's supposed to be here as a reactant, and it is. There's supposed to be 2 of them, and there is. Right? So I put a little blue box around it because, well, I'm really proud of that. All right, let's choose a different color. The next chemical in my target equation is a C2H6 gas. So again, if I look through all of my givens, I can see that C2H6 gas is here. Now you can also see that you have not 1, but 2 issues. First issue, wrong number. I need 1 of them, but this equation has 2. Okay, so it's not the right number. I can turn the 2 into a 1, right? Because you're not just allowed to multiply everything by a number, you're also allowed to divide everything by a number. So if I wanted to turn this 2 into a 1, I can divide everything by 2. Divide by 2, divide by 2, divide by 2, divide by 2, and divide by 2. The other issue that I have here is that I need the C2H6 to be a product, and my C2H6 is a reactant. It's on the wrong side of the equation. Now, I can take the entire equation and reverse it, but I have to change the sign. So my negative will become positive. So you can see here I've made some jot notes, right? I've made some notes on my equation to say what I'm doing. I'm dividing everything by 2. I am going to reverse it, and I've made a note to myself that I am changing the sign. This is why I like to rewrite them, because I've made a lot of changes, and it's easier to see the changes if I rewrite it. Okay, so let's write down our products first because they're going to become reactants. 4 divided by 2 gives me 2 carbon dioxide gases. 6 divided by 2 gives me 3 water gases. And my reactants become products. 2 divided by 2 gives me 1 C2H6 gas, which is perfect because I only wanted 1. And 7 divided by 2 gives me 3.5 oxygen gases. Okay, that's not overly nice. But for Hess, you are going to find that you're going to end up with decimal coefficients all over the place. Okay, we'll just work with them. It's one of those facts of the problem. So my delta H was negative, but it will become positive, and I do have to divide it by 2. So 3,119.8 divided by 2 gives me 1,559.9 kilojoules. And at the end, when I add up all of my equations, I am going to add up all my delta H's. And if one of them is just kilojoules, it's not kilojoules per mole, then really the rest are just going to be kilojoules as well. Okay? And again, let's take our red marker and let's put a box around this thing, right? It was important enough for me to go hunting for it, so let's put a box around it. All right, I'm feeling very good. I've worked my way through 2 of my given equations, right? I'm getting myself set up. So let's look at the last chemical in the target. The last chemical in the target is an H2. So if I look through all of these chemicals, I see that H2 only shows up here. Okay, now this is an H2O. It does have an H2, but that's not what I'm looking for, right? I'm looking for an H2 without the O. Now, if I look at the H2, I can see that the number is good. I need one of them, and I have one. So that's perfect. But I can see that the location is an issue, right? It should be a product, but I have it as a reactant. So what I'm going to do is I'm going to reverse this reaction, which means I'm going to change the sign. So again, let's write out what we got. Products become reactants, so H2O gas, and the reactants become products. So H2 gas plus a half an O2, let's call it a 0.5 of an O2, gas. And my delta H changes sign. So it was negative, but it becomes positive. So 285.8 kilojoules. And let's put a nice little green box around the H2. Now, I have reorganized all three of the givens, right? I've made changes to all three of them. So now I anticipate that when I add them all together, the things in the boxes will stay, because I need the things in the boxes, but everything else should cancel out and go away. That's what I'm anticipating. Now, when you go to add things, we should divide reactants versus products. Okay, reactants on this side, products on that side. Think of it in the terms of math. Let's say that I told you that you had x plus 2 equals y plus 2. If you have the exact same thing on both sides of a chemical or a math equation, you're allowed to cancel it, right? Plus 2 and plus 2, they just cancel out, so x equals y. A similar thing happens in the world of chemistry. If a chemical shows up as both a reactant and a product, you are allowed to cancel it out. Okay? So let's talk about our oxygens. I've got 4 O2 gases here. And if I look on the product side, I have 3.5 oxygens plus a half of an oxygen. Right? The oxygen showed up in two different places, but on the product side, I have a total of 3.5 plus 1/2. 3.5 plus a half is 4. So I got 4 oxygens on the product side. I've got 4 oxygens on the reactant side. So they cancel out. If we talk about carbon dioxide, I've got 2 carbon dioxide gases as products. I've got 2 carbon dioxide gases as reactants. They're exactly the same. There's 2 of them. They're both gases. They're both CO2s. They're identical and they're on both opposite sides. So they cancel. Okay, let's talk water. I've got 4 water gases as products. If you look over here on the reactant side, they're in 2 different places, but you have a total of 4, right? You got 3 water gases here, plus 1 more water gas here, right? Really one of them. So you got 4. If you got 4 on both sides, those 4 cancel with those. So if you look at your equations, the only thing that I wanted left was inside the boxes, right? I wanted the CH4, the C2H6, and the H2. And if you look here, you can see that everything that was not in a box is canceled. So when I add them up, what's the only thing left on the reactant side? Canceled, 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 canceled. The only thing I have left is the 2 CH4 gases, which is what I wanted. If you look on the product side, what do you have left? Canceled, canceled. Oh, I have this C2H6 gas. Canceled, canceled, and I have this H2 gas. When I take these 3 equations and add them up, virtually everything cancels out, and the only thing that I'm left with is the pieces that I wanted. And the really cool thing about adding chemical reactions is that if you add the chemical reactions, you can add the delta H's. So the delta H for this reaction would be 1780.8 negative plus 1559.9 plus 285.8. My decimal's hard to see, but there was a decimal. And so that gives me 64.9 kilojoules. So the heat that goes with this particular reaction is this. Now, the main reason why we would use Hess's law to calculate this rather than using like a calorimeter, because what you could do is take your methane gas, put it in a calorimeter, and actually measure the heat as the reaction does this. The problem is this reaction doesn't like to actually work, right? In the world of thermochemistry, exothermic reactions tend to happen really easily. Burning things is exothermic, and if you've had any experience with like barbecues or campfires or matches, you know that burning things is pretty easy. It's spontaneous. It just naturally happens. Most things that are endothermic with a positive delta H, those reactions tend to be non-spontaneous. They tend not to want to happen. So this reaction here would probably not happen or not happen very quickly, which is why we would calculate it rather than actually attempting to do it in a calorimeter. But that's Hess. You're going to modify your given equations so that way when they add, they give you your target equation and they give you the heat that goes with it. All right, so let's say that we try a second one. If we do the exact same thing that we did in the first one, this is my target equation, H2 plus Cl2 turning into 2HCl. I'm going to attempt to match each chemical in my target equation with its counterpart down here in the given equations, because that'll tell me how I need to modify the given equations. Do I need to flip them? Do I need to multiply them by 2? What do I need to do? Okay, so the first chemical in my equation is an H2. So if I look through my givens, I can see that H2 shows up right here. Okay, now two things that we're looking for. Is it in the right place and does it have the right number? It is in the right place. I need it to be a reactant and it is a reactant. Okay, that's excellent. Unfortunately though, the numbers are not right. I need one of them and I currently have 2. That's an easy fix. Divide it by 2 and that'll turn it into a 1. But it does mean that you're going to have to divide everything by 2. So divide by 2, divide by 2, divide by 2, divide by 2, and divide by 2. Now, if you're doing these problems and when you start canceling stuff out, you find that something doesn't cancel out perfectly, the most likely place that you made a mistake is right here. Right? When I'm dividing everything by 2, it's very easy to miss one. So I could be like 2 divided by 2 is 1, 2 divided by 2 is 1, 3 divided by 2 is 1.5, 2 divided by 2 is 1, and then 4. Right? I forget to divide this one by 2. So if you find in the end that things are not canceling out as you expect them, this is most likely where you made your mistake. You forgot to divide one out of like everything. Okay, so I'm going to rewrite that because I like rewriting them. 2 divided by 2 gives me 1. So CH2, Cl2, and a liquid is important. 2 divided by 2 is 1. So that gives me an H2 gas. 3 divided by 2 is 1.5, O2 gases. For these, we're willing to accept decimal coefficients. 2 divided by 2 gives me 1 CO, Cl2 gas. And 4 divided by 2 gives me 2 H2O liquids. My delta H is 805 divided by 2. So that would be what? 402.5. It was negative, so it stays negative. Now, if you are a significant figures person, when you divide this by 2, okay, the 2 basically has an unlimited number of significant figures because it's exactly 2, 2.00000. So when you divide this by 2, if you started with 3 sig figs, you should only have 3 sig figs. Okay, but for now, I'm just going to leave it as a 0.5. And I love my little boxes. Blue box around the H2. Let's put a little blue box around my H2. Perfect. All right, second chemical on my list is a Cl2 gas. So if I look through my equations, I can see that Cl2 gas is right here. Now you can see that this Cl2 gas has 2 issues. First one, there's two of them, right? I only need one, but there's two. The second issue is that I need it to be a reactant, but here it's a product. Okay, so it actually has two different things that I'm going to have to fix. Let's fix the two first. I can turn a 2 into a 1 by dividing by 2. But it does mean that I'm going to have to divide everything by 2. Now, this oxygen had nothing in front of it. If there's no number in front of it, the number is a 1. But it also means that I'm going to have to reverse the whole thing, right? Because I need it to be a reactant rather than a product. Which means that this nice positive 210 is going to become a negative 210. Okay, so there is a sign change. And it's for this problem here where there are so many changes, that's the reason why I like to rewrite. Okay, so if I rewrite that, my products become reactants. So 2 over 2 is 1 water, so that's an H2O liquid. The 2 over 2 is 1, so that's 1 Cl2 gas. And the reactants become products. So 4 divided by 2 is 2 HCl gases. And 1 divided by 2 is a 0.5 of an O2 gas. And the delta H. It was positive, so now it's going to be negative. And if I divide 210 in half, that gives me 105 kilojoules. And again, let's put a nice little box around the Cl2. Because I worked really hard to make it 1, and I worked really hard to put it in the right place. Right? So I'm going to put a little red box around it, kind of like a gold star. All right, last thing in my target equation is 2 HCl's. So if I look through all of these, I can see that my HCl is here. Now, you should be thinking, hold on a second. This is an equation that I've already done stuff with, right? I've already reversed it and I've already divided it by 2. Which means the HCl should be in the perfect place and it should have the perfect number, right? When I did 4 divided by 2, that gave me 2, and I needed 2. When I reversed it, it became a product and I needed a product. You can see in this equation that it's already in the perfect place. So when I changed this equation for the Cl2, I was also secretly changing it for the HCl. Okay, so both of these now are in the right place. Now there's a bit of a rule for Hess's law. If I give you 3 equations, you've got to use all 3 equations, which means that this last equation here, it's put there purely to help stuff cancel out. Okay? The only reason why it's there is to help things cancel. Now the problem is, the technique that we've developed is work your way through the given or the target equation and then make the given equations match it, right? That's how we did the first one. We modified each one so that at the end, everything in our target equation matched something in a given equation, right? We knew what we had to do to all 3. For this one, I don't know what I have to do to that first equation. I know that I need to use it. I also know that it's probably not going to be used exactly as it's written, right? It's going to have to be modified to cancel stuff out. So what I'm going to do, I'm going to leave space here to write it because I know that I am going to use it, so I'll leave some space. And what I'm going to do is start the cancellation process to kind of see if I can get a handle on what I need to do to this last equation. Okay, so let's separate reactants versus products. Anything that shows up as both a reactant and a product need to cancel. Okay, so let's talk about this CH2Cl2. In my target equation, there is no CH2Cl2 liquid, right? It doesn't show up, which means that this has to cancel out because I'm not allowed to leave it because it's not in my target equation. So it's got to go away. But if I look on my product side, I've got a COCl2, I've got some waters, I got some oxygens, but that's it. I have nothing to cancel out with this. There's like no piece over here that matches it. So that tells me what I have to do to the last equation. For the last equation, that last equation is going to have to give me a CH2Cl2 liquid here because I need one on the opposite side to cancel, right? I have to have one here to cancel out. So that tells me what my last equation is doing. So if I look at the last equation, that last equation does have a CH2Cl2 right here. There you go. I need to have one of them, right? Because in order to cancel, there's 1 and 1. And there is. That's good. And it needs to be a product. And here it is, a product. So it turns out that I didn't actually have to make any modifications to this equation. This one is written exactly as it should be. Now that's rare. That does not happen very often. Usually you'll have to flip it to get the thing in the right place, or you'll have to multiply it by a number. But for this one, in order to cancel this out, I need a match here on the product side, and the last equation actually does give me a match on the product side. So let's write out the equation. COCl2 gas, an H2O liquid. I've already written this piece down, and an O2 gas. And the delta H doesn't change at all because I didn't change the equation at all. So 95 kilojoules. Now, if I have written this last equation in the right way, then things should cancel out perfectly, right? So those already cancel out. Okay, see how I have a COCl2 here and there's no COCl2 in my target equation? That means it has to cancel. So if you've got one of them on the product side, you need one on the reactant side, right? COCl2 gas, COCl2 gas, one of them and one of them cancels. All right, 2 water liquids. I got 2 liquid waters here. There's no liquid water in my target equation, so it needs to cancel. If you look on this side, there's only 1 liquid water here, but there's also 1 liquid water here. There's 2 of them. So if you got 2 liquid waters, they cancel out with 2 liquid waters. And if we do oxygens, this is 1.5 oxygen gases. This is half of an oxygen gas. And this is 1 oxygen, right? So you got a total of 1.5 on the reactant side, and you got a total of 1.5 on the product side. So they cancel. And again, expect it because is there any oxygen gas in my target equation? No. So if I look at it, everything that needed to cancel here did. The only 2 things left are the H2 gas and the Cl2 gas. On the product side, everything canceled except for the 2HCl gas. And this is exactly what I wanted. So if I added all 3 of these equations to get my target equation, then I need to add all 3 of the delta H's. So this would be a minus 402.5 plus a minus 105 plus 95. That gives me a minus 412.5 kilojoules. And if you're not worried about significant figures, that is a beautiful answer for this, right? That is the heat that is associated with that reaction. If you are a significant figures person, okay, let's go back and make a couple of edits. This only had 3 sig figs. Therefore, this should have been rounded off to a negative 403 kilojoules. Right, so that should have been that. Which would have given you an answer of minus 413 kilojoules. And if you are adding things up, it is all about the decimal places. No decimal places, no decimal places, no decimal places. So your answer should have no decimal places. So for this particular problem, if you were following significant figures, you should get minus 413 kilojoules. If you are not worried about sig figs, then you'll probably end up with negative 412.5 kilojoules. But this is the heat associated with this reaction. All right. Now, when you do these problems, the majority of them, most problem sets will start with questions like this, where everything in the target equation matches to the givens. So that way, all of the givens get changed, and you just add them up. as you move through whatever problem set or worksheet you have, you're going to start to move into these, where you do have like a given equation, and the only purpose for it is to go in at the end to cancel stuff out. So let's see if we can practice another one of those, because those do tend to be a little bit harder because you will have this leftover equation that you have to figure out what to do with. Okay, so if we take a look at this one, my target equation is taking some sulfuric acid, turning it into SO3 gas and H2O gas. And just like every other problem so far, I'm going to work my way through the target equation and attempt to modify my givens to match it. So if I take a look at my H2SO4 liquid, and I look down through all of my equations, I find that I have an H2SO4 liquid right here. Now, that's good. I need to have one of them, and I have one of them. That's good. The not so good part, I need it to be a reactant, but it's listed as a product. But after a couple of examples, you should be thinking to yourself, that's not really a big problem. All I need to do is reverse this and change the sign. So let's write that out. That would give you, write the product first, H2SO4 liquid, turning into, write your reactants, H2S liquid plus some 2O2 gases, and the delta H was negative, but now it's a nice positive 255 kilojoules. And let's put a very nice little blue box around the H2SO4. Okay, next chemical in my target is an SO3 gas. So if I look down through, looking for an SO3, I can see my SO3 is right here. Well now, I believe that this may be a little bit of a present for you, because you need it as a product, and it is a product. You need it one of them, and there is one of them. This equation is perfect, exactly as it is. So when I go to write it down, I'm just going to literally rewrite it. So my H2S gas plus 2O2 gas turning into an SO3 gas plus an H2O liquid. And because I didn't change the equation at all, I don't change the delta H, minus 207 kilojoules. And let's put a nice little red box around the SO3 gas. There we go. It's always nice when one of the given equations just stays the same. It's like a little present. All right, last thing in my target equation is an H2O gas. Now you have to be careful because water shows up in this problem many times. There's a water here, there's a water here, and there is a water here. Right, so water shows up in a lot of places. That's why I was saying earlier that the state is important. This is a water gas. If I look through all of the waters, the only water gas in the entire problem is here. Right, that's a water liquid, that's a water liquid. That's not what I'm looking for. So I got a water gas here. So it's a little tricky that I did throw in some water liquids to try and throw you off. But once you realize that it's water gas and it only appears here, then you realize that this is another little present. You need it to be a product, and it is a product. You need to have one of them, and there is one of them. So this is another one that you get to just write down. So that's an H2O liquid turning into an H2O gas. And because you didn't change the equation, the delta H doesn't change, 44 kilojoules. And let's put a nice little green box around my H2O gas. Now we've hit a similar problem to the last time, right? I have worked my way through my entire target equation. I have found all three of the chemicals that I need, but I have a leftover equation. Now, you're not allowed to ignore the leftover equations. The leftover equations have to be used, and their entire purpose is to cancel stuff out. So I'm going to leave a space here for that last equation. Okay, so let's start talking about canceling stuff out. Everything that I want is in a box, right? Sulfuric acid, SO3, water, they're all in boxes. So all of these things that are not in boxes need to cancel out. Okay, so you can see that some of them start to cancel. I've got two O2 gases here. I've got two O2 gases here. They're both O2s. They're both gases. They both have a 2 in front. They're exactly the same, so they cancel. Look at the waters. I got an H2O liquid here. I've got an H2O liquid here. There's one of them. They're both liquids. That's a perfect match, so they cancel. Nice. Now, this is where the problem gets easy to make a mistake. You can see that I have an H2S here and I have an H2S here. There's one of them and one of them. So initially, they do look like a matching pair that you should be able to cancel out. But they're not exactly a matching pair because this one's a liquid and this one's a gas. If they have different states, then they are considered different and you can't cancel them. Okay? So if I wanted to cancel out this H2S gas, there needs to be an H2S gas on the opposite side. Right? The only way I can cancel it is if it appears on opposite sides of the equation. Same number, same state. This now tells me what my last equation has to be. Right? I need to have an H2S gas on the product side. So if I look at the last equation that was given, here's an H2S gas. I need one, there is one. I need it to be a product, and it is a product. Okay, so it's another one of those where that last equation is perfect, no changes, right? This chemical is in the right place to do the canceling. Okay, again, that doesn't happen a lot. So if we rewrite the rest of it, H2S liquid, and because I'm not making any changes, my delta H is 19.5 kilojoules. So H2S gas cancels with H2S gas, and now I've got something to cancel out my liquid, right? H2S liquid on the product side and H2S liquid on the reactant side cancel. If you look through at the reactant side, everything has canceled except H2SO4 liquid, which is what I wanted. If you look through the product side, cancel, 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 cancel. The only two things left are SO3 gas and H2O gas, which again is two things I want. And if you add up all of the equations, then you should add up the delta H's as well. So I've got 255 plus a negative 207 plus 44 plus 19.5 gives me a value of 111.5 kilojoules. Now, if you're not worried about significant figures, then that's a perfectly good answer. But if you are doing significant figures, adding is all about the least number of decimal places. No decimals, no decimals, no decimals, one decimal. The least number is none. So this really should round off to having no decimal places. So if the number you're chopping off is 5 or bigger, that means you have to round up. So if you're doing significant figures, you would round it to 112 kilojoules. This is the amount of heat that is associated with this reaction. This is the enthalpy change that goes with this reaction. All right, let's take a look at one more. Now I'm hoping if you've watched all of them so far, you can see that a pattern is developing, right? You start by working your way through your target equation. So I got 2 aluminum solids. If I look down through my equations, I've got 2 aluminum solids. Then you're like, this is perfect. I've got 2 and I needed 2. I needed them as reactants, and they are reactants. So this first equation is perfect. Okay, so let's just rewrite the first equation. 2 aluminum solids plus 6 HCl aqueous turns into 2 aluminum chloride aqueous and 3 H2 gases. If you don't change the equation, you don't change your delta H. So that's a minus 1,049 kilojoules. And we went to the trouble of putting a little blue box around our 2 aluminums, so let's keep our little blue box around our 2 aluminums. Okay, second chemical in my target equation. 3 Cl2 gases. So if I look through my equations, I'm looking for Cl2 gases. There's my Cl2 gas. I need it to be a reactant, and it is a reactant. That's good. I need 3 of them, but I only have 1. So I'm going to multiply everything here by 3. 3 H2s, 3 Cls, 6 HCls, times it by 3, and 3 times the enthalpy change. Okay, so if we rewrite, that gives me 3 H2 gases, 3 Cl2 gases, turning into 6 HCl gases, and the delta H is 3 times as much. I'm going to need my calculator for that. 1845 negative times 3. That's a minus 5,535 kilojoules. And again, let's put a nice little box around my 3 Cl2s. All right, last chemical here in my equation is 2 aluminum chloride solids. So if I go looking, you can see that I've attempted to fool you the same way. Aluminum chloride does show up multiple times, but this one is aqueous, this one's aqueous, this one's solid. The solid one only appears in one place, right here. Now, I've also decided to make your life hard by messing with pretty much everything. It should be a product, but it's a reactant. You should have 2 of them, but there's only 1. Okay, but I can make it 2. Multiply that by 2, that by 2, and that by 2. I can also make it a product by changing the sign, right? So I'll reverse this, flip it, and change that negative to a positive. And really, in these problems, that's the only way I can mess with a problem, right? Or mess with a given. I can move it to the opposite side, and I can mess with the number, right? Because the only 2 things you're allowed to do are flip and then multiply or divide by a constant. So let's flip it and multiply. So my aluminum chloride aqueous was a product. It's now going to be my reactant, 2AlCl3 aqueous. The 2 aluminum chloride solid was a reactant, now going to be a product, so 2AlCl3 solid. And the delta H was negative, but it's going to be a positive, and you're multiplying by 2, so 646 kilojoules. Everything in my target equation has a box around it, so oops, let me put a little box around it because I'm pretty happy with my boxes. So everything in the target equation has a box, and I have all of them. But I do have a leftover equation. That leftover equation is purely there to cancel stuff out. So the way we deal with it, leave a space and start canceling. Anything on the reactant and product sides that are identical, cancel out. So if we talk about gas, like the 3H2 gas here. 3H2 gas is a reactant, 3H2 gas is a product. They're identical and they cancel. 2 AlCl3 aqueuses, 2 AlCl3 aqueuses. They're identical and they cancel. I've got 6 HCl and 6 HCl. Initially, they look the same. They look like they should be able to cancel, but this one's an aqueous and this one's a gas. They don't match perfectly. So they're going to tell me what I'm doing with my last equation. Okay, so let's talk about this one here. Let's put it like in a little cloud. If I want to get rid of my 6 HCl aqueuses, I'm going to have a matching 6 HCl aqueuses, but on the opposite side, right? These were reactants, so these are products. This tells me what I need to do to the last equation. So if I look at my last equation, I do have the aqueous as a product, right? I need it to be a product, and it is a product. But I don't have the right number. I need to have 6, but there's only 1. So what I'm going to do is multiply everything in this by 6. So I'll multiply this by 6. Okay, so 6 times HCl gas gives me 6 HCl gas. 6 times the HCl aqueous, I've already got that. And my delta H will stay negative because I didn't flip it, but it is going to be 6 times 74.8 negative. That's a negative 448.8 kilojoules. Okay, these cancel. And you can see that my 6HCl gas here now have something to partner with, right? They're a matching pair. They're 6, they're both gases, so they cancel. Now, if you look at your reactant side, everything is canceled except for the 2 things I want. The 2 aluminum solids and the 3 Cl2 gases. If you look on the product side, everything has canceled except for the one thing I wanted, 2 AlCl3 solids. And if you add up all of the chemical reactions, that means you can add up all the delta H's. So 1049 negative plus 5535 negative plus 646 plus 448.8 negative. That gives me a negative 6,386.8 kilojoules. If you're not worried about sig figs, that's an excellent answer. If you are worried about sig figs, no decimal places, no decimal places, no decimal places, 1 decimal place, so your answer should have no decimal places. If the number that you're getting rid of is bigger than 5, you round up. So for significant figures, this would be a minus 6,387 kilojoules. And this is the heat or the enthalpy change associated with this chemical reaction. Now, there are some Hess's law problems that are a little bit more complex than that. If the chemicals that you are looking at in these boxes, your target ones, shows up in more than one of the given equations, then that causes a bit of an issue. Now, if the Hess problems that you're being given on your worksheets or your problem sets match these, then you're probably good. But if you do find that things in your target equations show up in more than one of your givens, I do have a second Hess's law video that'll help you with those. That video is meant to be just for the more extreme or the more advanced problems. So thank you for joining us here at Chemistry with Dr. Clark.